In this video, we'll go over the solution of how to scale an H100 pH transmitter. For this instrument, the range is -2 to +16 pH, and that range is the physical measurand that the sensor is measuring. The output of the instrument is 4 to 20 milliamps. As we have just seen, the range of this instrument is -2 to +16 pH. The output is a 4 to 20 milliamp signal. And the resistance value of the resistor we will be using in this current loop is 250 ohms. To make it more clear, we have a pH sensor, which is an instrument, and it's using a 4 to 20 milliamp loop. And the 4 to 20 milliamp loop is the type of communication signal. The wires physically running from the instrument meet up at a 250 ohm resistor, and the controller measures a voltage across that resistor. Remember that inside the pH instrument is a pH sensor as well as signal processing circuitry. The signal processing circuitry does things such as amplify, filter, and convert the signal from analog to digital. The instrument also creates and transmits the 4 to 20 milliamp signal, which is sent to the 250 ohm resistor. Now we'll perform the scaling. We use the linear equation of y equals mx plus b, where y equals the engineering units, or the real-world physical phenomenon we're measuring, otherwise known as the measurand. M equals the slope of the curve, x equals the input, or the signal being input into the controller, and b is the intercept. So why do we need to find m and b? These are the variables we need to feed into the controller so that it is able to do a few things for us. 1. Display engineering units. For example, if we are measuring 1 volt, then we know that we are measuring -2 pH. Or if we're measuring 5 volts, then we know we're measuring 16 pH. We also want to ensure that the controller has accurate values so that it may perform the calculations we tell it to correctly. Let's perform our scaling calculation. So y, again, is our engineering unit, or our range, which is -2 to 16 pH. X is our input. That means the input to the control system, which is different than the output of the instrument. In a 4 to 20 milliamp loop, we output 4 to 20 milliamps out of the instrument, but but we input the 1 to 5 voltage because we are measuring across a resistor. So let's use our system of equations to solve for M and B. We'll start at the lower end of the range. So we replace Y with -2 equals M times 1 volt plus B. At the high end of the range, we have 16 equals M times 5 plus B. We'll multiply the bottom equation times -1 to get -16, -M5, and -B. Then we'll add the two equations together to get -18 equals -4. Divide both sides by -4, and M equals 4.5. Now we'll plug M into the first equation. We have -2 equals 4.5 times 1 plus B. Subtract 4.5 from both sides, and B equals -6.5. Now we've found our slope and our offset. So into our control system, we'll enter -2 for the lower range, 16 for the high range, 4.5 for the slope, and -6.5 for the offset. Elsewhere in the system, we may already have listed the 1 to 5 volt input. We can also see a graph of the data we've just created. We have a linear scale starting from 1 volt going to 5 volts, increasing from -2 pH all the way up to 16 pH. And for example, you can see if we are reading a voltage of 2.78, that means we are measuring 6 pH. Final takeaways here are knowing that scaling is a way to correlate the engineering units with the controller input. So in this example, that's pH and voltage. What do you need to know in order to scale? Well, you need the range of the instrument, the input to the controller, and you also need the value of the resistor that you're using in the 4 to 20 milliamp loop. And that's all. The math is easy. Basically, you're figuring out what data you need from the data sheet.